So welcome back, everyone. Do you have any questions that we did on last night's class? Did you enjoy the video I showed you of the conference I attended on the imaging of a black hole? I know some of the terminology in the video can be mind-boggling. So in the video, I posted Mr. Groenewald asked that I post a link for the conference where it was discussed on the WhatsApp group. So if you watch from minute 30, you can see what's going on. But they talked about using the Roach 2 DBE to do their recording of the data. That's the Roach 2 digital backend, and that is one of the systems I'm involved with and working on. So it's cool. So with the Event Horizon telescope, a lot of people got together around the world to image the black hole. One of the persons you will meet in your third year and honors degrees is Prof. Roger Dean. He was involved with the program in imaging the black hole while creating the software to image the black hole. So now we've done the path where we go from a supernova to a neutron star, but now we need to go from a supernova all the way to a black hole. So the first idea of a black hole was first proposed by an English astronomer, John Michell, in 1784. Mitchell's simplistic calculations assumed that such a body might have the same density as the Sun, and concluded that such a body would form when a star's diameter exceeds the Sun's by a factor of 500, and the surface escape velocity exceeds the speed of light. And then, in 1915, Albert Einstein developed the theory of general relativity, where the theory shows that gravity influences the motion of light. So the image on the right is probably one of the most iconic photos of Albert Einstein. A couple of years ago, that the original image went on auction for a huge amount of money. Then on the left is an image you're probably familiar with, and that is Einstein in his 20s. In 1905, Albert Einstein determined that the laws of physics are the same for all non-accelerating observers, and that the speed of light in a vacuum was independent of the motion of all observers. This was the theory of special relativity. It introduced a new framework for all of physics and proposed new concepts of space and time. Einstein then spent 10 years trying to include acceleration in theory and published his theory of general relativity in 1915. In it, he determined that massive objects cause a distortion in space-time, which is felt as gravity. And then Einstein come up with the field equation for general relativity. So you don't need to know this formula at all. I just included it as background knowledge for this lecture. So this is also something you don't need to know at all, but I thought this was fun to show you where he came to the equation E equals mc squared. So the T right here. I'm not exactly sure what that T is. It's been a while since I've went through this. I can't remember by memory. So you don't need to know this at all, but this is the derivation for E equals mc squared, and I thought this would be something interesting to tell you. Oh, and now I remember what this T is. That is, if I'm correct, that's time dilation. So we start by noting that energy in the integral form with respect to distance. So kinetic energy can be derived. So have you ever done the first principles on kinetic and potential energy? That's something you will probably do within the next semester. But here we can see where F is the force in direction of displacement, ds, and s is the distance over which the force acts. So using Newton's second law of motion, force F can be shown as, so anything that we do is, we write F as dmv over dt, and now we substitute this into the equation of F over here. So now kinetic energy can be written in this form. So we can now simplify the equation, so getting rid of everything. So now we can integrate by parts this equation. So when we integrate by parts, we are left with mc squared, mc0 squared. So the result shows the kinetic energy of a body is equal to the increase in its mass as a consequence of its motion multiplied by c to the power c squared. So this so the equation can be arranged as this. So the kinetic energy is decreased so that k equals 0. So that means, in other words, the body contains energy, beginning energy in stationary relative to its frame, and will have a mass of m0. This is called a rest mass. So we can write this. So because we have rest mass, we can simplify the equation as this, and this is E equals mc squared, and E equals mc squared can be rewritten as this. Yes, minute physics, I agree. So this is just something interesting of how we got to it. So after Einstein published his theory, Karl Schwarzschild, so one of you asked if we're going to learn about the Schwarzschild radius, this is where it's coming in now, found a solution to the Einstein field equations, which described the gravitational field of a point mass and a spherical mass. A few months after Schwarzschild, Johannes Drost, a student of Hendrik Lorentz, independently achieved the same result for a point mass. So here is Einstein's field equation for general relativity, and as we have seen here, Karl Schwarzschild and Johannes Drost both solved this equation. So here we can see what it means. So here it is. So the T is the stress energy tensor, Newton's gravitational constant, scalar of curvature, Ricci curvature, metric sensor, cosmological constant. So here you don't have to know this formulas, just for background information. And then Stephen Hawking gave a more solid mathematical understanding to the concept of a black hole. So the EHD Event Horizon Telescope that we saw in last night's talk is an astronomical collaboration that has formed to continue the steady long-term progress on improving the capacity of very long-base interferometry. So before I continue, I've now talked about this before, but who of you is not familiar with very long-base interferometry? Okay, so let me explain very long-base interferometry. The acronym is VLBI. So what very long-base interferometry does is it takes these different telescopes. So these are the telescopes of the event horizon. Then all of these telescopes observe the object you're looking at. So we use VLBI for a lot of things, different objects. So say, for example, these telescopes, if they are connected, let's get a pen out. This will form a leg. That 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 will form a leg. A leg. A leg. A leg. A leg. Another leg. Another leg. Another leg. Another leg. So where these red is, that is basically a virtual telescope we're creating. Guys, just excuse me for 30 seconds. I'm just going to open up for my cat. Ah, so sorry about that. So I'm back. So what happens is with VLBI, so we have all these legs, so we call them baselines from that runs from each telescope to all the other. So with these baselines, we can construct a virtual telescope that is the size of these baselines. So you can think about we can construct a virtual mirror basically that is the size of these legs. So therefore, by using VLBI, we can basically construct a virtual telescope that is the size of Earth. And with that, we can get more information from an object. So does that sort of explain VLBI? Awesome. So, sorry guys, my phone is ringing. I'm just going to tell the person I'm in class. Sorry about that. So this is one of those days when everybody's trying to get a hold of me. So yes, like in the lecture we seen last night. So we use this around the world with all other telescopes, and it's a very important principle of doing astronomy. So these telescopes that was selected for the Event Horizon telescopes has something unique in common. These telescopes are in high enough and dry enough places that they can detect X-rays, and so they don't get interference from the atmosphere. So one of the problems is getting data from the telescopes. There's a telescope in Antarctica. I don't know if you guys is familiar with that. And so the observations being done here, they actually have to fly from South America to Antarctica, get our hard drives, and fly back. So back in the early 1900s, after Einstein's field equations, this is an artist's representation and the best representation we had of what a black hole might look like. So very few, so let's go back here in the article. No, that's actually not true. The only thing why, so I don't know if you know about it. There's a research base in Antarctica, and the research base needs volunteers to conduct research, carry out experiments. So every year they change out the crew of the research base. So I don't know if you guys are familiar. Do you guys know that South Africa has a research ship? So let me quickly see if I can find you an image of the research ship. I'm just quickly going to get you an image of it. Yes, the SAO Gullis. So there's actually a second one, the SAO Gullis 2 as well. So let me quickly show you a picture of it. So this is the SAO Gullis. A better image is probably this one. So the SAO Gullis and the SAO Gullis 2 is basically one giant research ship. So the entire ship is basically a giant lab and has different labs in it. And that is used to conduct research at sea. But a ship is also used to take. No, I've unfortunately not been on the SAO Gullis. My girlfriend will kill me if I disappear for a year. So what happens is you can apply to be on the SAO Gullis or the Antarctica research base. So for the Antarctica research base, you apply for the position. So they first look at your qualifications and skill set. If you are selected for the qualifications and skill set phase and you go through, then they look at your physical health and fitness level. And then if you pass the fitness and health check, then you qualify to go for a research base. Then I wait for basically the summer months in Antarctica. Then you go onto the SAO Gullis. It's about a month's journey to Antarctica. Then you man the research base for a year. And then after a year, the SAO Gullis comes and picks you back up. And then it's about a month journey back to South Africa. I know a lot of people underestimate what SA is capable of. So then you can spend some time there. So for South Africa to enter it, you'll see the South African National Space Agency, or short SANSA, every year advertise they are looking for scientists and engineers for the next expedition to the Arctic base to man the Arctic base. And then you will be joined up with scientists and engineers from other countries, and you will all be doing experiments, working together, living together for a year, manning the base, and then after a year, the entire crew is swapped out again. And then you can also apply to work on the SAO Gullis. The SAO Gullis usually has mission from about 3 months to 6 months at sea. So after that image, the simulations predicted that the image of a black hole will look like something like this. And when the first image was captured, this is how it looked like. So basically the same as the simulation. So again, this comes down to what we learned in the first few lectures of this module, mathematical models. Everything comes down to our mathematical models of what we can observe and what we can predict. So To understand what's going on, so after the question, do these lectures cover everything we need to know for the test? Yes, the lecture slides cover everything we need to know for the test. So you all know we need escape velocity, so that's the speed needed to escape the gravitational pull of an object. So suppose you threw a baseball straight up. How fast must you throw it if it's not to come down? Of course, gravity will always pull back on the ball, slowing it. But if the ball is traveling fast enough to start with, it will never come to a stop and fall back. Such a ball will escape from Earth. To escape from Earth, a spaceship would have to leave Earth's surface at 11.2 kilometers per second. But if you could launch spaceships from the top of a tower 100,000 miles high, the escape velocity will only be 10 kilometers per second. So the higher you are, the more escape velocity you have. And those of you that watch SpaceX launches, you probably see that their spacecraft usually stabilizes at a speed of 27,000 kilometers per hour. Have you guys thought why it's 27,000 kilometers per hour? Yes, it is to achieve escape velocity, firstly, and then get into the correct orbital velocity. So if you could make an object massive enough or small enough, its escape velocity could be greater than the speed of light. Albert Einstein's theory of special relativity, published in 1905, says that nothing can travel faster than the speed of light. So even photons, which have no mass, would be unable to escape. Such a compact, massive object could never be seen because light could not leave it. Just an off-topic point of interest. Do you guys know, okay, if you think about Albert Einstein, we think of it as the father of relativity. But in fact, he was more known for his work on the photoelectric effect. So long before Einstein and relativity, the Reverend John Michell, a British gentleman astronomer, realized that this particular consequence of Newton's law of gravity and motion. In 1783, he pointed out that an object 500 times the radius of the Sun, but of the same density, would have an escape velocity greater than the speed of light. Then all light emitted from such a body would be made to return towards it. Michell didn't know it, but he was talking about a black hole. And yes, for which he won the Nobel Prize. If the core of a star contains more than 3 solar masses when it collapses, no force can stop it. It cannot stop collapsing when it reaches the density of a white dwarf, because degenerate electrons cannot support that weight. And it cannot stop when it reaches the density of a neutron star, because not even degenerate neutrons can support that weight. No force remains to stop the object from collapsing to zero radius. As an object collapses, its density and the strength of its surface gravity increase. If an object collapses to zero radius, its density and gravity become infinite. Mathematicians call such a point a singularity. So remember this definition for tests and exams, singularity. But in physical terms, it is difficult to imagine an object of zero radius. Some theorists believe that a singularity is impossible and the laws of quantum physics must somehow hold the collapse at a radius of roughly 10 to the power 20 times smaller than a proton. Astronomically, it seems to make little difference. If the contracting core of a star becomes small enough, the escape velocity in the region of space around it is so large that no light can escape. This means you can receive no information about an object or about a region of space near it. Because it emits no light, such a region is called a black hole. If the core of an exploding star collapsed into a black hole, the expanding outer layers of the star could produce a supernova remnant, but a core would vanish without a trace. So it's not just visible light that we won't be able to see. We won't be able to see anything coming from a black hole because electromagnetic radiation travels at the speed of light, and to escape the velocity of the black hole, you need to travel faster than the speed of light, so even electromagnetic radiation is not safe. In 1916, Albert Einstein published a mathematical theory of space and time that became known as the general theory of relativity. Einstein treated space and time as a single entity called spacetime. His equations showed that gravity could be described as a curvature of spacetime, and almost immediately the astronomer Karl Schwarzschild found a way to solve Einstein's equations to describe the gravitational field around a single, non-rotating, electrically neutral lump of matter. That solution contained the first general relativistic description of a black hole. And no rotating electrically neutral black holes are known as Schwarzschild black holes. In recent decades, theorists such as Roy Kerr and Stephen Hawking have found ways to apply the sophisticated mathematical equations of the general theory of relativity, electromagnetism, and quantum mechanics to describe charged, rotating black holes. For this discussion, the differences are minor, and you may proceed as if it's all black holes with Schwarzschild black holes. Schwarzschild's solution showed that if matter is packed into a small enough volume, then space-time curves back on itself. Objects can follow paths that lead into the black hole, but no paths lead out, so nothing can escape. Because not even light can escape, the inside of the black hole is totally beyond the view of an outside observer. The event horizon is the boundary between the isolated volume of space-time and the rest of the universe. And the radius of the event horizon is called the Schwarzschild radius, so we abbreviate it RS. A collapsing stellar core must shrink inside its Schwarzschild radius to become a black hole. So in this image, here we can see the singularity. Here's the Schwarzschild radius, and this is the event horizon. So in theory, if you're outside the event horizon, then you can escape the black hole or orbit the black hole. But if you're on the event horizon or closer, then you are pulled into the black hole. Although Schwarzschild's work was highly mathematical, his conclusion is quite simple. The Schwarzschild radius depends only on the mass of the object. So Rs equals 2gm over c squared. In the simple formula, g is the gravitational constant, m is the mass in kilograms, and c is the speed of light in meters per second. A bit of arithmetic shows that one solar mass black hole has a Schwarzschild radius of 3 kilometers. A 10 solar mass black hole has a Schwarzschild radius of 30 kilometers, and so on. Every object has a Schwarzschild radius determined by its mass. But not every object is a black hole. For example, Earth has a Schwarzschild radius of about 1 centimeter, meaning that it could become a black hole if you squeezed it smaller than that radius. It is a common misconception to think of black holes as giant vacuum cleaners that will eventually suck everything in the universe. A black hole is just a gravitational field, and at a large enough distance, its gravity is no greater than that of a normal object of similar mass. If the Sun were placed by a 1 solar mass black hole, the orbit of the planet would not change at all. So in this image, we can see if you fell into a gravitational field of a star, you would hit the star's surface before you fell very far. Because a black hole is so small, you could fall much deeper into its gravitational field and eventually cross the event horizon. At a distance, the two gravitational fields are the same. The figure illustrates this by representing gravitational fields as curvature of the fabric of space-time. Normal uncurved space-time is represented by a flat plane, and the presence of mass, such as a star, curves the plane to produce a depression. The extreme curvature around a black hole produces a deep funnel-shaped surface in the graphic representation. You can see from the graphs that the gravity of a black hole becomes extreme only when you approach it close. Now you can check off another misconception that might strike you as silly because of special effects in movies and TV. Some people think black holes should actually look like funnels. Of course, the graph of the strength of gravity around a black hole looks like funnels, but black holes themselves are not shaped like funnels. If you could approach a black hole, you might be able to see hot gas swirling inward, but you wouldn't be able to see the black hole itself. So what would happen if we would leap into a black hole? Before you can search for real black holes, you need to understand what theory predicts about a black hole. To explore that idea, you can imagine leaping feet first into a Schwarzschild black hole. If you were to leap into a black hole of a few solar masses from a distance of 1 AU, the gravitational pull would not be very large, and you would fall slowly at first. Of course, the longer you fell and the closer you came to the center, the faster you would travel. Your wristwatch would tell you that you fell for about 2 months by the time you reached the event horizon. Your friends who stayed behind would see something different. They would see you falling more and more slowly as you come closer to the event horizon. As explained by general relativity, time slows down in curved spacetime. This is known as time dilation. In fact, your friends would never actually see you cross the event horizon. To them, you would fall more and more slowly until you seemed hardly to move. Generations later, your descendants would focus their telescopes on you and see you still inching closer to the event horizon. You, however, would have sensed no slowdown and would conclude that you had reached the event horizon after about 2 months. Another relativistic effect would make it difficult to see you with normal telescopes. As light travels out of a gravitational field, it loses energy, and its wavelength grows longer. This is known as gravitational redshift. As you fell toward a black hole, your friends would need to observe at longer and longer wavelengths to detect you. While these relativistic effects seem merely peculiar, other effects would be quite unpleasant. If you were falling feet first, you would feel your feet, which would be closer to the black hole, being pulled in more strongly than your head. This is tidal force, and at first it would be minor. But as you got closer to the black hole, the tidal force would become very large. Another tidal force would compress you as both your left and your right side fell toward the center of the black hole. For any black hole with a mass like that of a star, the tidal forces would crush you sideways and stretch you lengthwise long before you reach the event horizon. So in this image, we can see leaping feet first into a black hole. A person of normal proportions left will be distorted by tidal forces on the image on the right long before reaching the event horizon around the typical black hole of stellar mass. Tidal forces would stretch the body lengthwise and compress it laterally. Friction from distortion would heat the body to high temperatures. So yes, you can think about this as spaghettification. The friction from such severe distortions of your body would heat you to millions of degrees, and you would emit X-rays and gamma rays. Some people have suggested that it's possible to travel through the universe by jumping into a black hole in one place and popping out of another somewhere far across space. That might make good for science fiction, but tidal forces would make up an unpopular form of transportation, even if it worked. You now know how to find a black hole. Look for a strong source of X-rays. It may be a black hole into which matter is falling and being heated. The first X-ray telescopes reached orbit in the 1970s, and that allowed astronomers to begin searching for evidence of black holes. They tried to find one or more objects that were obviously black holes. That very difficult search is a good illustration of how the unwritten rules of science help scientists to understand nature. A black hole alone is totally invisible because nothing can escape from its event horizon. But if matter flows into a black hole, it will whirl through an accretion disk and become hot enough to emit X-rays before it reaches the event horizon. An isolated black hole in space won't have much matter flowing into it, but a black hole in a binary system might receive a steady flow of matter transferred from the companion star. This suggests you can search for black holes by looking closely at X-ray binaries. Some X-ray binaries, such as Hercules X1, contain a neutron star, and they will emit X-rays much as would a binary containing a black hole. You can tell the difference in two ways. If the compact object emits pulses, you know it's a neutron star because the neutron star has a solid body within which powerful magnetic fields are generated. As the neutron star rotates, the magnetic field emits beams that sweep around the sky, producing pulses as they pass across Earth. A black hole inside its event horizon cannot emit regular pulses like those from a neutron star. Another clue depends on the mass of the object. If the mass of the compact object is greater than about 3 solar masses, it cannot be a neutron star, it must be a black hole. The first X-ray binary suspected of harboring a black hole was Cygnus X1, the first X-ray object discovered in the constellation Cygnus. It contained a supergiant star of spectral type B0 and a compact object orbiting each other with a period of 5.6 days. Astronomers suspected that the X-rays were emitted by matter from the star flowing into the compact object. That object is invisible, but Doppler shifts in the spectrum reveal the motion of the B0 star around the center of mass of the binary. From the geometry of the orbit, astronomers were able to calculate that the mass of the compact object had to be greater than 3.8 solar masses, well above the maximum for a neutron star. To confirm that black holes exist, astronomers needed a conclusive example, an object that couldn't be anything else. Cygnus X1 didn't quite pass the test when it was first discovered. Perhaps the B supergiant star was not a normal supergiant, and its portion of the system mass was incorrectly estimated. Or perhaps the system contained a third star. Either possibility would distort the analysis. At the time, astronomers could not conclusively show that Cygnus X1 contained a black hole. It took years of work to understand Cygnus X1. Further observations and analysis showed that a B0 star has a mass of about 25 solar masses, and a compact object is about 10 times the mass of the Sun. Astronomers conclude that matter flows from B0 star as a strong stellar wind, and much of that matter gets caught in a hot accretion disk about 5 times larger in diameter than the orbit of Earth's moon. The inner few hundred kilometers of the disk have a temperature of about 2 million Kelvin, hot enough to radiate X-rays. So here you can see an artist's representation. So the X-ray source Cygnus X1 consists of a supergiant B star, a compact object orbiting each other. Gas from the supergiant star, stellar wind, flows into the hot accretion disk around the compact object, and the X-rays astronomers detect come from the disk. So here we can see the object, its companion star, orbital period, and the mass of the black hole with the search of black holes. Someone's mic is unmuted. So another way to confirm that black holes are real is to search for evidence for their distinguishing characteristic, so event horizons, and that search also has been successful. So gas spiraling into an accretion disk grows hot, and as it nears the central object, a strong gravitational redshift makes it appear redder and dimmer. Systems containing a neutron star emit bursts of energy when the gas hits the surface of the neutron star, but such bursts are not seen for systems containing black holes. In those systems, the matter vanishes as it approaches the event horizon. This is a direct observational evidence of an event horizon around a black hole. So here we can see in this representation, matter spiraling into a black hole vanishes with no detectable bursts of energy, but with a neutron star, it's spiraling to the neutron star with a detectable burst of energy. So matter flowing onto a neutron star or into a black hole forms an accretion disk, and that can produce some surprising phenomena. Astronomers are just beginning to understand these peculiar effects. So we can detect jets of energy from compact objects. Observation shows that some compact objects are emitting jets of gas and radiation in opposite directions. These jets are similar to the bipolar outflows ejected by protostars, but much more powerful. And this is now leading up to gamma ray bursts. The Cold War played a minor part in the story of neutron stars and black holes. In 1963, a nuclear test ban treaty was signed, and by 1968, the United States was able to put a series of satellites in orbit to watch for nuclear tests that were violations of the treaty. A nuclear detonation emits gamma rays, so the satellites were designed to watch for bursts of gamma rays coming from Earth. The experts were startled when the satellites detected about 1 gamma ray burst a day coming from space. When those data were finally declassified in 1973, astronomers realized that the bursts might be coming from neutron stars and black holes. These bursts are known as gamma ray bursts, or abbreviated GRBs. So here we can see, altered by gamma ray detectors on satellites, observers used one of the VLT 8.2 meter telescopes on a mountaintop in Chile to image the location of a GRB only hours after the burst. The image at the top shows the fading glow of the eruption. The image at the top, recorded 13 years before, reveals no trace of an object at the location of the GRB. The Hubble Space Telescope image at the bottom was recorded a year later and reveals a very faint distant galaxy in the location of the GRBs. So here we can see visual during, you can see visual before, we can't see anything, and here we can all of a sudden see something. Gamma ray bursts are hard to study because they occur without warning and fade quickly. But starting in 1997, new satellites were put into orbit to detect gamma ray bursts. Their data showed that there are 2 kinds of gamma ray bursts. Short bursts lasting more about or less 2 seconds, but longer bursts can go on for tens of seconds, up to several minutes. Specialized space observatories now can detect bursts, quickly determining their location in the sky and immediately alert astronomers on the ground. When telescopes on Earth swiveled to image the location of the burst, they detected fading glows that resembled supernova. Stellar interior models indicate that a star more massive than some upper limit of about 20 solar masses can exhaust its nuclear fuel and collapse directly into a black hole. Models show that a collapsing star would conserve angular momentum and spin very rapidly, slowing the collapse of the equatorial parts of the star. The poles of the star would fall in quickly, and that would focus beams of intense radiation and injected gas that would blast out along the axis of rotation. Such an eruption has been called a hypernova. So here we can see the collapse of the core of a massive star begins along its axis of rotation. The rotation of the star slows the collapse of the equatorial regions. Within seconds, the remaining portions of the core will fall in, and beams of gas and radiation strike surrounding gas and generate beams of gamma rays along the rotation axis. The gamma ray burst fades in seconds, and hot accretion disk is left around a black hole. Short gamma ray bursts, on the other hand, don't seem to be associated with hypernova. Some repeat, and these repeating bursts seem to be produced by a neutron star with magnetic fields 100 times stronger than that in a normal neutron star, dubbed magnetars. So remember the definition of a magnetar. These objects can produce bursts of gamma rays when shifts in the magnetic field break the crust of the neutron stars, causing star quakes and release large amount of energy. So in this image we can see an artist's representation. Some neutron stars appear to have magnetic fields up to 1,000 times stronger than those in a normal neutron star. These magnetars can produce bursts of gamma rays when shifts in the magnetic field rupture the rigid crust of the neutron star. Not all gamma ray bursts are produced by magnetars. Some bursts have occurred in parts of distant galaxies where you would not expect to find the young massive stars that produce magnetars or hypernova, and the afterglows don't resemble fading supernova. These bursts may be produced by the merger of two neutron stars or a neutron star and a black hole that orbited each other, radiated orbital energy as gravitational radiation, and spiraled into each other. Such a collision would cause a violent explosion as two objects merge to form a new larger black hole. The gamma ray burst and fading afterglow from a neutron star plus black hole merger should be different from that produced by the merger of two neutron stars. Could a gamma ray burst occur near Earth? The nearest known binary pulsar is only about 3,000 light-years from Earth. If a gamma ray burst occurred at that distance, the gamma rays would shower Earth with radiation equivalent to a 10,000 megaton nuclear blast, comparable to a full-scale nuclear war between superpowers. So the largest single bombs ever made released less than 100 megatons of energy. The gamma rays could create enough nitric oxide in the atmosphere to produce intense acid rain, and also would destroy the ozone layer, exposing life on Earth to deadly levels of solar ultraviolet radiation. Gamma ray bursts can occur relatively near Earth, as often as every few 100 million years, and could be one of the causes of the mass extinctions that show up in the fossil records. So, how do we detect gamma rays? Are you guys all familiar with the HESS telescope in Namibia? So the HESS telescope is an array telescope, same as the Meerkat telescope or the CAT-7 telescope, only with a much fewer telescopes. And the telescope is designed to detect gamma rays from space, and it is actually quite successful. So here we can see an image of one of these gamma rays, gamma ray detecting telescopes. So now we are coming to an end with our discussion on black holes. And here we can see an image of the disk's underside, the accretion disk, the Doppler beaming image of the disk's far side, photon ring, and the black hole shadow. So when the black hole was imaged in 2017, a few scientists reacted to the first image. So, Professor Brian Greene, a theoretical physicist, it is hard to express how utterly remarkable and astonishingly delightful it is that mathematical scribblings can predict something as bizarre as black holes. And then, looking into the skies with sufficient diligence, we found them. And this is Einstein's field equation, just in a different form. Neil deGrasse Tyson. Scientists, we've produced the first ever image of a supermassive black hole, 55 million light years away, and response from public is ooh. Scientists, we've concluded that humans are catastrophically warming Earth. Response, that conflict with what I want to be true, so it must be false. Then Bill Nye. How can we see a star that gives off no light of its own? Take a look. And then he posted a link to the image captured by the Event Horizon Telescope. And so, ladies and gentlemen, do you have questions on black holes and neutron stars? You guys have no questions, or is this a little bit of information overload? Yes, Mr. Bonolo.
Black holes, do they absorb particles in a spherical manner, like in every direction?
Yes, they. So the easiest way to let me get a blackboard. It will be easiest to describe. So.
And the result of the what is it? Is it disk?
Yes. So if this is the black hole, and the entrance of the black hole, or according to the rotation, is going into the black hole, so into the screen, it means it doesn't matter from which side you are from the black hole. The accretion disk that we see will be around a certain part of the black hole, but the event horizon so the event horizon can be is in this plane, in this plane, in this plane, in this plane, because we can see everything around a black hole as a sphere. So it doesn't matter in which axis, which direction it's approached from, it will still be influenced by the black hole because it's a sphere.
So the accretion disk is because of angular momentum?
Yes, angular momentum. So let's remove this. So if this is our black hole, and this is our accretion disk around it, and the accretion disk, for example, is coming from a companion star falling into, what's happening due to angular momentum, the material falling into the black hole is speeding up, meaning the angular momentum is becoming higher the closer you get to the black hole. And due to that, there's more friction between the particles, so you get more heat, and therefore you can emit X-rays, and we can detect the X-rays.
Okay, thank you, sir.
Awesome. You guys have any other questions? So, how does Hawking radiation work? So Hawking radiation is something we are going to discuss in one of our other lectures. But what's happening basically with Hawking radiation, we can discuss that in a later section. But the sweet and short of it is the matter falling into the black hole in the accretion disks emits radiation called Hawking radiation. But that is something we are going to discuss literally in the next few chapters.
Sir,
Yes.
can there be a huge black hole such that if something is past the event horizon, it will not be spaghettified?
The larger it is, the more spaghettified it will become.
Oh, okay.
So now question, do we have something that can counter the pull of the black hole? So no. So currently there's nothing known to us that can counter the effects of a black hole. So now that we've discussed all these different objects, the birth of stars, the death of stars, compact objects, now we can start looking at a whole and we can start looking at different galaxies. So our galaxy is called the Milky Way galaxy. So in this chapter, we're going to look at the discovery of a galaxy, the structure of a galaxy, spiral arms and star formation, the nucleus of a galaxy, and then the origin and history of the Milky Way galaxy. So this is the famous image of how the universe began. So it started out with the Big Bang, and then on the time scale, it is 13.8 billion years, still expanding. So here we can see modern galaxies starts to appear around about here. So now we're going to start look at how this happened. So looking at our galaxy, we are located right here in the outer rim. So something interesting. So in astronomy, you can either look something, we call it in small scale, so that is different individual objects, so such as stars, planets, magnetars, pulsars, black holes. But if we look at a galaxy as a whole and study galaxies, we call that field of study cosmology. So one of my colleagues, he's a Canadian, he usually makes a joke and says, cosmologists are the gynecologists of astronomy. So this here is the Fermi All-Sky survey of the Milky Way galaxy. So here we can see so we can think about the galaxy as a disk. And here we can see, if you look into the center of the galaxy, the disk straight on, and we can see the center of the galaxy has a lot more objects and therefore radiates more energy. So this right here is the Meerkat telescope, and which will surprise you, in this image, each dot you see here in this image above the Meerkat is a different galaxy. So this is the Meerkat survey of the center of our own galaxy. So here we can see the center of our own galaxy. Right here we can see a supernova remnant. And something we still can't explain that we are trying to explain is what these filaments are. There are a few theories, but we are not 100% sure what these filaments are. So you've traced the life stories of stars from their birth in clouds of gas and dust to the depths as white dwarfs, neutron stars, or black holes. Now you are ready to step back and view stars in the vast communities called galaxies. This chapter focuses on our home galaxy, the Milky Way, and addresses 5 important questions. What is the evidence that we live in a galaxy? What is the evidence that our Milky Way galaxy is a spiral galaxy? What are the spiral arms of the Milky Way and other spiral galaxies? What is in the nucleus of the Milky Way galaxy? How did the Milky Way galaxy form and evolve? So this is just something interesting I thought to show you. So I know in previous lectures I talked about how we do tracking and telemetry on spacecraft. So these are one of the giant lasers we have at Hadrow, and we use it to do tracking and telemetry on spacecraft. So this is a 1.3 gigahertz pulsed laser. So here we can see the laser firing over the telescope. So we literally fire the laser to a satellite. The laser beam reflects back. We know what the speed of light is, the speed of the laser. We record the time for the laser to be reflected back, and then from there we can calculate the orbit of a satellite accurately to 3 millimeters. So from there we can let organizations, countries, institutes that have satellites in orbits know if their satellite is still in the correct orbit, if it's drifting out of orbit, that they need to adjust the orbit so they don't lose the satellite. And when new satellites are launched into orbit, we do priority tracking missions to help guide the satellites into the correct position. Just another image of the laser. So this laser was actually designed and built by Roscosmos, the Russian space agency, and we operated for him. You will learn in this chapter how evidence reveals that you are inside a great wheel of stars, a galaxy. The Milky Way galaxy is over 80,000 light years in diameter and contains more than 100 billion stars. It is your galaxy because you live in it, but you're also a product of it. Because the stars in the Milky Way galaxy make many of the atoms in your body, you can begin this chapter by pondering the notion that the stars belong to you. But when you reach the end of the chapter, you may realize that you also belong to the stars. It seems odd to say that astronomers discovered something that is all around us. But it isn't obvious that we live in a galaxy. You might ask, how do we know what our galaxy is like? Nobody has ever seen it from the outside. Finding the evidence to answer that question was one of the greatest adventures in astronomy. Since ancient times, humanity has been aware of a hazy band of light around the sky. So I'm sure if all of you were in a dark place, such as the Karoo, you looked up in the night sky and you will see a fuzzy band in the night sky. Is everybody still there? Awesome. So in this image, nearby stars look bright and people around the world group them into different constellations. Nevertheless, the vast majority of the stars in our galaxy that are visible from Earth merge into a faintly luminous path that circles the sky, the Milky Way. This artwork shows the location of a portion of the Milky Way near a few bright winter constellations. So in a textbook, you can look at figure 12.5 and the star charts in Appendix B to locate other sections of the Milky Way galaxy. Then in image B, the Andromeda Galaxy, also known as Messier 31, a spiral galaxy about 2.5 million light years from Earth, looked like our galaxy would appear if you could see it from the same distance. The two oval patches to the upper right and lower right of the main galaxy's central bulge are small satellite galaxies. So here is a small satellite galaxy, another small satellite galaxy, and that orbits the main big galaxy. The ancient Greeks named the band of galaxies. So are all galaxies in a disk shape like the Milky Way galaxies? Yes, they are all in a disk shape. We will discuss why that is in a moment. But the shape inside the disk can differ a little bit. The ancient Greeks named the band of galaxies Kuklos, the Milky Circle. The Romans referred to it as the Via Lactea, meaning Milky Road or Milky Way. It was not until Galileo used his telescope in 1610 that anyone realized the Milky Way is made of a huge number of stars. Almost every celestial object you can see with your unaided eyes is part of the Milky Way galaxy. The only exception viewable from Earth's northern hemisphere is the Andromeda Galaxy, also known as Messier 31, which is barely visible as a faint patch of light in the constellation Andromeda. You will learn later in this chapter that our galaxy is also a spiral galaxy and seen from a distance would look somewhat like Andromeda Galaxy. So if you're ever in a very dark place and the horizon to the east is not blocked by anything, to the south, it's not blocked by anything, and you can see very close to the horizon something that would look like a small cloud, and that is actually the Andromeda Galaxy you are seeing. But again, you have to be at places that's extremely dark to be able to see that. So this is how the Andromeda Galaxy and our own galaxy will look like. Galileo's telescope revealed that a glowing Milky Way is made up of stars, and later astronomers realized that the Sun must be located in a great wheel-shaped cloud of stars, which they call the star system. The star system appears from our location inside as the band of the Milky Way encircling the sky. So here we can see Thomas Wright. Are you guys familiar with Thomas Wright? So, in 1750, Thomas Wright, drawing on the technology of the time, referred to the wheel-shaped star system as the grindstone universe, by analogy with the thick discs of stone used in mills. Wright used the term universe because so far as was known at the time, the Milky Way star system was the entire universe. In the late 18th centuries, astronomers Sir William Herschel and Caroline Herschel, Sir William Herschel's sisters, set out to map the three-dimensional distribution of stars in the Milky Way. They assumed that they could see to the other boundaries of the Milky Way in all directions, and hypothesized that by counting the number of stars that were visible in different directions, they could find a relative distance to the edge of the star distribution. If they saw many stars in one direction, they reasoned that the edge of the Milky Way in that direction is far away. If their telescope revealed fewer stars in another direction, they concluded that the edge must be closer, calling their method star gauging. They counted stars in 683 directions in the sky and outlined a model of the star system. So in image A, we can in 1785, William Herschel published this diagram showing the shape of the star system as if it could be viewed edge-on from outside. Then image B, the sun is located near the center of this grindstone model universe. So seen edge-on, Herschel's model of the star system was very irregular disk. And then the disk shape of the star system reminded astronomers of the thick millstone disks used for grinding flour. Their data indicated that the stars were arranged in a disk shape with the sun near the center. In some directions, the Herschel saw very few stars, and these holes in the sky produced great irregularities along the edge of the diagram. The model proposed by the Herschels was widely accepted and studied by other astronomers. The Herschels were not able to measure the size of the star system, but later researchers attempted to do so. By the early 20th century, astronomers had concluded that a star system's disk is about 10 kiloparsecs in diameter and 2 kiloparsecs thick. So a kiloparsec is 1,000 parsecs. The Herschels assumed that they could see to the edge of the star system, but that was not correct. They were actually seeing only as far into the Milky Way as the interstellar dust permitted. At the time the Herschels did their work, astronomers did not understand that the interstellar medium partially blocks the passage of light. Because the Herschels counted roughly similar number of stars in most directions around the Milky Way, they incorrectly concluded that the sun is near the center of the star system. Furthermore, the holes in the sky observed by the Herschels are not empty, but are now known to be especially dense interstellar clouds, completely blocking the view of stars behind them. Modern astronomers know that the Milky Way galaxy is much larger than was first thought, and that the sun is not at its center. How the human race realized the truth about the location of the universe is a story that begins with a woman studying stars that pulsate and leads to a man observing distant star clusters. So now we're going to learn about and talk about variable stars and distance estimates. It is a common misconception that the stars are eternal and unchanging, but astronomers have known for centuries that some stars change in brightness. Of course, novae and supernovae appear, grow brighter, and then fade. But many stars change periodically, growing brighter, then fainter, then brighter, and so on. Some of these variable stars are eclipsing binaries, but some are stars that pulsate like beating hearts. The period of pulsation is the time it takes a star to complete a cycle from bright to faint to bright again. In 1912, Henrietta Leavitt was studying a star cloud in the southern sky known as the Small Magellanic Clouds. So remember the lecture where we can discuss the Small Magellanic Clouds? Awesome. So on a photographic plate, she found many variable stars, and she noticed that the brightest had the longest periods. She didn't know the distance to the cloud, so she couldn't calculate absolute magnitude. So now everything's coming together. We learn about absolute magnitudes as well. But because all of the variables she was observing are in the same star cloud and can be assumed to be at about the same distance, she concluded that there is a relationship between period and luminosity. The variable stars Leavitt saw, called Shepaids, are named after the first such star discovered in Delta Shepay. Many Shepaid variables are known today. They have pulsation periods from 1 to 60 days and lie in a region of the HR diagram known as the instability strip. So here we can see our wonderful HR diagram again. So more massive stars are more luminous and larger, so they pulsate relatively slowly. Observations of Delta Shepay shows the shape of an actual light curve. So here we can see the shape of the actual light curve. And this part right here in the HR diagram is the instability strip. Shapades are clearly giant and supergiant stars. A related kind of variable, RR Lyra stars, are named after variable stars RR in constellation Lyra. They have a pulsation period of about half a day and lie at the low luminosity end of the instability strip. Type 1 Shapades have chemical compositions similar to that of the Sun. Type 2 Shapades and the RR Lyrae stars are poor in elements heavier than helium. Stars in the instability strip are unstable and pulsate because a layer of partially ionized helium in the star's atmosphere can absorb and release energy like a spring. In very hot stars, the layer is too high to make the star unstable, and in very cool stars, the layer is too low. Stars in the instability strip have this layer in just the right place to make them pulsate as energy flows out of their interiors. As stars evolve across the HR diagram into the instability strip, they become unstable. They stop pulsating when they evolve out of the strip. So these two definitions, you can also keep them in mind for tests and exams. Massive stars are very luminous, and they cross the instability strip higher in the HR diagram. Because these massive stars are larger, they pulsate slower, just as large bells vibrate slower and have deeper tones. Lower mass stars are less luminous, cross the instability strip low in the HR diagram, and being smaller, pulsate faster. This explains why the long period Shapades are more luminous than the short period Shapades. Leavitt first noticed what is known as the period luminosity relation in 1912. In this image, we can see the period luminosity diagram is a graph of brightness of variable stars versus their periods of pulsation. You could plot brightness as luminosity, but because the diagram is used in distance calculations, it is more convenient with absolute magnitude on the vertical axis. Modern astronomers know that there are two types of Shapades, something that astronomers in the early 20th century could not recognize in their limited data. Humanity's understanding of the nature of the Milky Way began to change radically around the year 1920, when an astronomer named Harlow Shapley discovered how big the star system really is. Besides being one of the turning points of modern astronomy, Shapley's studies illustrates one of the most common techniques in astronomy. If you want to understand some of the basic ways astronomers find out about the universe, then Shapley's part of the story is worth following in detail. So here we can see his third 60-inch reflecting telescope. You learn in Chapter 10, Section 1 that star clusters come in two quite different types, open clusters and globular clusters. Shapley began his research on the star system by noticing that although open star clusters are scattered all along the Milky Way, more than half of all globular clusters lie in or near the constellation Sagittarius. The globular clusters seem to be distributed in a great cloud with a center located in the direction of Sagittarius. So here we can see open clusters lie along the Milky Way all around the sky. Here the red dots are globular clusters. Shapley assumed that the orbital motion of these clusters is controlled by the gravitation of the entire star system. And for that reason, he concluded that the center of the star system could not be near the Sun, but must lie somewhere towards Sagittarius. To find the distance to the center of the star system, and thus the size of the star system as a whole, Shapley needed to find the distance to the star clusters. But that was difficult to do. The clusters are much too far away to have measurable parallaxes. They do, however, contain variable stars, and those were the beacons Shapley needed to find the distances to the clusters. Shapley now knew about Leavitt's work on Shapade variable stars. Shapley and other astronomers realized that the Shepherds could be used to determine distances if their true luminosities could be discovered. But because Shepherds are giant and supergiant stars, they are relatively rare. None lies close enough to Earth to have a measurable parallax, but their proper motions, apparent slow movements across the sky, due to the motion through space, can be measured. The more distant the star is, the smaller its proper motion tends to be. So proper motions contain clues to distance. Shapley found 11 Shepherds with measured proper motions and used a statistical process to find their average distance and thus their average absolute magnitude. Then he could replace Leavitt's apparent magnitudes on the vertical axis of the period luminosity diagram with absolute magnitudes representing the true luminosities. So here we can see this image again, now with absolute magnitude. All of the stars in the diagram was thus calibrated as standard light sources that astronomers could use to find distances. Calibrations like this one are important tools in science. So how do you take the temperature of a vat of molten steel? Say that Shapley calibrated the Shepherds for the determination of distance, meaning that he did all the detailed background work to determine the luminosities of Shepherds. After that, he and other astronomers could use his calibrated period luminosity diagram to find a distance to other Shepherds without repeating detailed calibration. Calibration is actually very common in science because it saves a lot of time and effort. For example, engineers in steel mills must monitor the temperature of molten steel, but they can't dip a thermometer. Instead, they can use handheld devices that measure the color of molten steel. You recall from Chapter 6, Section 2 that the color of a black body radiation is determined by the temperature of the body emitting it. Molten steel emits visible and infrared radiation that is nearly perfect black body radiation. So the manufacturer can calibrate the engineer's device to convert the measured color to temperature displayed on digital readouts. The engineers don't have to repeat the calibration every time. They just point their instrument at a molten steel and read off the temperature. Astronomers have made the same kind of color temperature calibration for stars. As you read about in science, notice how calibrations are used to simplify common measurements, but notice, too, how important it is to get the calibration right. An error in calibration can throw off every measurement made with that calibration. Once Shapley had calibrated the period luminosity relation, you could use it to find the distance to any star cluster in which you could identify those types of variable stars. By taking a series of photographic plates over a number of nights, Shapley was able to pick out the variable stars in a cluster, measure their average apparent magnitude, and find their periods of pulsation. Knowing that, you could read the absolute magnitude of the period luminosity diagram. With the apparent magnitude and the absolute magnitude, he could calculate the distance to the star cluster. Shapley later wrote that it was late at night when he finally plotted the directions and distances to the globular clusters on graph paper and found that, just as he had supposed, they formed a great swarm whose center lay mainly thousands of light years in the direction of Sagittarius, confirming his suspicion that the center of the star system was not near the Sun, but was far away in Sagittarius. In Shapley's study of globular clusters showed that they were not centered on the Sun at the origin of this graph, but rather from the great cloud centered far away in the direction of Sagittarius. Distances on this graph are given in thousands of parsecs, corresponding to Shapley's original calibration that produces distances more than 2 times larger than modern values. Then in image B, looking towards Sagittarius at visual wavelengths, you see nothing to suggest that this is the center of our galaxy. Interstellar dust and gas block your view. Only the distribution of globular clusters told Shapley that the center lies in this direction. He found the only other person in the building, a cleaning lady, and the two stood looking at his graph as he explained that they were the only two people on Earth who understood that humanity lives. Not near the center of a small star system, but in the suburbs of a vast wheel of stars. It is important to note that there were problems with Shapley's calibrations and distance determinations. Shapley was able to observe the globular clusters at great distances because they lie outside the plane of the galaxy and are not dimmed much by the interstellar medium. But the Shepard stars he used for calibration mostly lie in the plane of the galaxy and were strongly affected by extinction. Also, Shapley did not know there are several types of variable stars, but the ones he used for their distance estimates were different from the ones he used for the calibration. Consequently, his estimate of the size of the galaxy, shown in figure 12.6, was bigger than the modern value. Nevertheless, he got a main point right, that we are thousands of light years from the center of the galaxy. Building on Shapley's work, other astronomers began to suspect that some of the faint patches of light visible through telescopes were other star systems. Within a few years, they found evidence that the faint patches of light were indeed other galaxies, much like our own Milky Way galaxy. Today, the largest telescopes can detect an estimated 100 billion galaxies similar to our own. Our home galaxy is special only, and that is our home. Shapley's studies of star clusters led to the discovery that we live in a galaxy and that the universe is filled with similar galaxies. Like Copernicus, Shapley moved us from the center to the outskirts. A careful analysis of the structure of the galaxy would tell you the details about our real location. Astronomers commonly give the diameter of the Milky Way galaxy as approximately 25 kiloparsecs, or 80,000 light years, and place the Sun about 2/3 of the way from the center to the edge. So here we can see the central bulge, another disk, and the Sun. So if we look at it from the side, this is where the Sun will be, our central disk, and this is the halo of the galaxy, and these are globular clusters. Now we're going to start to look at different components of a galaxy. The disk of a galaxy is often referred to the disk component. It contains most of the galaxy's stars and nearly all of its gas and dust. Because the disk is home to the giant molecular clouds within which stars form, nearly all star formation in our galaxies take place in a disk. Most of the stars in a disk are middle to lower main sequence stars like the Sun. A few are red giants and white dwarfs, and fewer still are brilliant blue O and B stars. Those hot, massive stars are rare, but they are so luminous that they provide much of the light from the disk. Although astronomers can survey the locations and distances of the stars, they cannot cite a single number of the thickness of the disk because it lacks sharp boundaries. Also, the thickness of the disk depends on the kind of object studied. Stars like the Sun, with ages of a few billion years, lie within about a 500 parsec above and below the central plane. In comparison, the youngest stars, including the O and B stars at the gas and dust from which stars form, are confirmed to be a thin disk extending only about 50 parsecs above and below the plane. In proportion to its diameter of about 25 kiloparsecs, the disk of the galaxy is thinner than a pizza crust. So here we can see again the central bulge of the galaxy. This is the galactic plane, and here is the Magellanic Clouds, our satellite galaxies. Looking in here, we can see different stellar dust emits different blackbody radiation and glows at different wavelengths. So here we can see the Orion molecular clouds, the galactic plane, the Taurus molecular clouds, and so on. If you look up or down out of the galaxy's disk, you are looking away from the dust and gas, so you can see into the galaxy's halo, a spherical cloud of stars and star clusters that contain almost no gas and dust. Because the halo contains no dense gas clouds, it cannot make new stars. Halo stars are old, cool, lower main sequence stars, red giants, and white dwarfs. It is difficult to judge the extent of the halo, but it could have as much as 10 times the diameter of the visible disk. Around the center of a galaxy lies the center bulge, a flattened cloud of billions of stars about 6 kiloparsecs in diameter. Like the halo, it contains little gas and dust. Astronomers often refer to the halo and the central bulge together as the spherical component of the galaxy. The central bulge is the most crowded part of the spherical component. The central bulge, visible above and below the plane of the galaxy and through gaps in the obscuring dusk, consists mostly of stars that are old and cool like the stars in the halo. So again, here we can put it together. So here is our spiral galaxy, the Milky Way, the central bulge. Sun is located here, and yet this is part of the disk. So from sideways, we can see the halo, this patchy area, globular clusters, and then our galaxy sideways and our disk. The halo includes more than 150 globular clusters, each of which contains 50,000 to a million stars, in a sphere a few tenths of parsecs in diameter. You can tell the average age is about 11 billion years from the position of the turn-off points in the HR diagrams. Orbital motions are quite different in the two components of the galaxy. Disk stars follow nearly circular orbits that lie in the plane of the galaxy. So here we can see circular orbits. And then stars in the halo have randomly orientated, highly eccentric and elongated orbits around the center of the galaxy. Halo stars and globular clusters, however, follow highly elongated orbits tipped steeply into the plane of the disk. Though the diagram in the previous figure shows these orbits as simple ellipses, that is not quite true. The gravitational influence of the thick bulge forces them into curves that do not quite return to the same starting point. The dramatic difference between the motions of halo stars and disk stars will be important evidence when you consider the formation of the galaxy later in this chapter. This analysis of the components of the Milky Way galaxy may leave you wondering about one important question. How much matter does a galaxy contain? To answer that question, you can measure the galaxy's rotation. So, ladies and gentlemen, we are going to end the lecture right here. So next week's semester test will be everything we've done in a semester up until tonight's lecture. So if you have no further questions, you are more than welcome to log off. Otherwise, I will see you in next week's class. So next week, Monday, we will continue with this lecture. Next week, Tuesday, I will go through the memo of the mock test with you. I will release or upload the mock test tomorrow for you guys. Then we'll go through the memo and you will be able to ask questions if you struggle with the work. And then we will do a little bit of new work as well. Awesome, guys. So if you have no questions, you're more than welcome to log off. Good luck with the semester test. If some of you guys are writing tomorrow, good luck with the rest of the week. And I will see you all next Monday. So no, you're not going to be writing about a moon, because in later chapters we're going to do an entire section just on the moon itself. Pleasure. Yes, Mr. Bonoa.
Say, for interest's sake, don't you think every galaxy bends its own space-time? Because like they
Yes, it
are.
does. Because what we will learn in next week's chapter, and every galaxy contains a supermassive black hole, and that is what keeps everything together. So everything in a galaxy orbits around a black hole, and that's why it bends space-time.
Are they relatively in the same direction? Everything in the galaxy.
It's not in the same direction. So the
Okay.
galaxy is a sphere that's expanding. So you can imagine, or you can imagine the universe as a balloon, and the balloon is being filled with air and is expanding in every direction.
Every direction. Okay. So since now the center is a black hole, isn't it crashing the galaxy somehow? Maybe shrinking, like everything's being absorbed.
No, because if everything is in stable orbits around the black hole,
Okay. Okay. Thank you, sir.
it's a pleasure. So if there's no further questions, I'm going to stop the recording.